Good afternoon, everyone. Topic is finite element analysis. A little bit of a survey and overview of this technique, which I would hope that you will find out more about by taking a course in it. Because more than likely, you're going to be called upon to use this in your practice as an engineer. If you do any kind of design work, that'll certainly be true. So here's the context in which I'm presenting it. And I'm not going to try to teach you the theory of finite elements. We're going to talk about how to use it properly and what some of the limitations are. So at the base of this is the need to understand the fundamentals that we've been talking about for the past 7 weeks. The fundamentals of stress analysis, fatigue analysis, calculating safety factors, Goodman line analysis, all that sort of thing still applies, even more so when you start using this very powerful tool. The problem with the classical methods we've been talking about is that if the geometry of my parts gets too complex, then it's very difficult to use these simple techniques because, what's the area moment of inertia of something that looks like a crankshaft? That's a difficult problem to solve. And when we run into those, we need a tool like FEA. Now, FEA was invented around 1956, I think is the right year. Didn't really come into serious use until, I want to say 40 years ago or something in that ballpark. I first got an opportunity to use it when I was working at a fairly big company that was pretty well off at the time. They're now bankrupt, but they had money then, and so they could afford to buy this very expensive software. In fact, they didn't buy it, they rented it. And I remember I had to get in my car and drive to another building someplace, which was the computer company that was renting them the time on the huge mainframe to run this thing, and it was an absolute nightmare. You've probably never seen a key punch that makes punch cards, but that's what you had to use to put in the data. And you had to type in every bloody number for the whole mesh, and of course you made dozens of errors, maybe hundreds of errors, and it was just absolutely a nightmare. I gave it up as a bad job after a little bit of a try. We're much better off now because we have packages that really do it nicely, and many of you may have already used them. The concept is extremely simple. The execution of it is not, but as long as we have powerful computers, that sort of takes care of itself. So we've talked throughout this course on how to solve for the stresses in simple shapes, prisms, rectangular prisms, round things, cylinders, and that sort of thing. And in the bad old days, before we had this FEA tool, what you had to do was simulate your crazy shaped part as a collection of these all put together so that you could calculate for the bits and pieces what the stresses were. In other words, I'd simulate something that was not quite a cylinder as a cylinder and that sort of thing. So there's a lot of error involved in that. But what this FEA business does is it lets us break the part down into a very large number of simple shapes, and I'll show you some of those shapes in a minute. But they essentially could be rectangular blocks, is one possibility, okay? And they're tiny. So I can put thousands of those in, and this is called a finite element, that's the name. Well, it's an element, and there is a finite number of them, though it's a large finite number, that's the name. And since we know how to calculate the stresses and deflections and all that stuff of a rectangular thing, we simply solve a lot of simultaneous equations to find it for all of these little bricks at once. That's essentially the basis on which FEA works. This shows examples of such a mesh, which is what the collection of elements is called, a mesh. And they've been applied to the three principal parts of a reciprocating engine, the piston, the connecting rod, and the crankshaft, all of which have geometry complicated enough to make it very tough to do any kind of what I call classical stress analysis, or deflection analysis for that matter, on these. So what's been done here is it's been broken up into a very, very large number of little rectangular cubes. They're not really cubes, they're shaped, but you get the idea. And thus we can have a set of equations, which might be 10,000 equations when we're all done, that we'll solve simultaneously in the computer. And it's very important to remember this point. And I'm sure you've encountered this before. Garbage in, garbage out. You know, I don't know where I found this quote, but I thought it was cute. You put garbage in a computer, nothing comes out but garbage. But this garbage, having passed through a very expensive machine, is somehow ennobled and no one dares criticize it. And not only that, you can get it out to 10 decimal places if you'd like, or maybe 15. It looks very impressive, but it could well be total garbage. And if you don't set the problem up correctly, I guarantee it will be garbage, okay? And you'll just take yourself down the garden path. So this is something you have to be very cautious of, and that's where understanding the fundamentals comes in. Okay, so you need to keep in mind the stuff you've learned in all your fundamental classes when you use this tool. So if you set it up improperly, you're going to get junk. And you need to understand the theory we've been talking about to interpret the results. Like von Mises stresses, for example, what the hell do they mean? That's what it's going to tell you have. It's going to give you the von Mises stresses. It's going to give you the principal stresses, too. But most importantly, I have to understand what its limitations are, so that I don't misuse it and exceed its limitations, in which case I will get very bad results. So this is as far as I'm going to go into the theory with a very simple model like this. This is the concept. It's just going to be applied thousands of times to a whole bunch of these. So we're going to consider each little element to be a spring. And in this simplistic example, we have a one-dimensional model. I can have a one-dimensional FEA, two-dimensional, or three-dimensional, with the complexity, of course, going up and the computation time going up and the need for more computer power going up as I add dimensions, okay? But this problem is simple enough to actually solve by hand for a small number of elements. So we have what are called one-dimensional elements that are represented by springs, and we have a force being applied at one node, N-O-D-E, and another force at another node, and of course those nodes connect up to the other elements in the system, and each of these nodes will have a displacement represented here as u sub I and u sub j for the two different ends of the element. And so that's our simple free body diagram. So the element will be given a number, which I've represented as h. And so it's simply an exercise in writing the equations associated with some of the forces. And there's no sum of the moments here because we have a one-dimensional system. So some of the forces on this thing, and we have two equations, one for the left end, one for the right end, and we can put those in matrix form, which in compact matrix notation looks like this. We have what's called a stiffness matrix with the k's. That would be the k of the spring. And we have a displacement vector here and a force vector, and that's the whole story. Now, if we look at the one on the right, where we have two of these elements, we're just going to get more equations. So we have two equations now, actually four total, two of these matrices. We have to know something, of course, going into the problem. Typically, you know what some of the forces are, because you're putting forces on the system. We also may know that the displacement is 0 at some location, because it's tied down. That's a fixed point. Okay? So we'll be setting various displacements to typically 0 if it can't move there. And we'll be putting a force on the other end. So in my simple spring example, I might say that the left-hand side, that U1 is 0. That's my fixed end. I guess I show it fixed in the right-hand picture, don't I? And then I will tell it I have a load F on the other end over there. So those are my inputs. And from that calculation and the set of equations solved simultaneously, I want to find out what U2 is and U3 is. Right? And also what the internal forces are. So what I'm going to get out of that is that F1 and F2, which represent these different locations. This would be the reaction force over here, intermediate force here. In this simple system, they're all going to be the same value. But that won't be true in a general, especially a two- or three-dimensional system. So I can do some equation substitution. I'm combining those equations to get a larger matrix equation. Again, this is my stiffness matrix, so-called here, my displacement vector, and my force vector. In compact matrix notation, it looks like this. It's a linear problem, at least in the simplest form of FEA. We can also do nonlinear FEA. It just takes more computation time. But I'm showing you the linear approach here. So we're going to solve these equations simultaneously and get a set of answers. Okay? That's That's basically it. Any questions about what's going on behind the curtain in that respect? All right, so you have a collection of element types you can pick from. And I've broken them down by 2 dimensions. I shouldn't use the word dimension because one of the parameters is dimension. 2 different flavors, let's call it. I've got dimension as across on the rows, and I've got order of the element as, displacement in the columns, and the order is in the rows, the way I've got it arranged, okay? So displacement is pretty obvious. I've either got 1D, 2D, or 3D. What is meant by order is the simplest would be a linear element, and this is the one I was just showing you that I represented as a spring. It's called a line element, okay? All it can do is pass a force in one direction. Now, when would you use that? If I'm analyzing a truss in a bridge, because the assumption is the forces exist only in the truss elements, and they're in one direction, which happens to be the angle of that truss element, right? And then I move to 2D, and I can have a 2-node line as well, still in 2D. I can have a 3-node triangular or a 4-node quad, and you can keep going, of course, and have, you know, pentagonal and hexagonal and all that stuff. But this is usually complex enough to do what you need. And then these, of course, become 3-dimensional when I make a brick out of the quad and I make a tetrahedron, or tetrahedron, out of the triangle. And they're given nicknames, quad, tet, and brick in the trade. Now, these are linear because it's assumed that the distribution along the edges is linear. I can bump that up, and I can keep going as far as I want in that direction by adding more intermediate nodes. So if I add intermediate nodes within the element, so they look like this, now I have what's called the quadratic element, because now the edges of those can assume parabolic shapes, right? Because I have 3 data points. And these will give me better results. So the more order I have, the more accurate approximation, and it's always going to be an approximation, I'm going to end up with. But the cost, of course, is computation time. In the early days of FEA, that was a big deal because computers were slow. Now, with the very high-speed computers we have available for very low cost, you can sort of have your cake and eat it too, and put some of these high-order things in and not have to wait 2-3 days, literally, to get the results. So in terms of which of these are good and which are bad, most experts seem to agree that you should not use the 3-node triangular, and you should not use the tetrahedral. And the reasons I go into in the book in some detail. Let me just say here, for the sake of brevity, you get less than good accuracy with those particular choices of elements. There are some exceptions in which you can use those. We'll talk about those later. However, if you move up to the quadratic, then the tet is fine, and then triangular is fine, because now I can see the variation along the edges sufficiently well. So it's only these linear versions that are considered to be too crude. Unfortunately, in my experience, most of the, I think this is changing because the code's getting more and more sophisticated all the time, but a lot of the FEA solvers that do auto meshing, they create the mesh for you at the push of a button, which is really neat. You take your solid model from SolidWorks, Pro-E, whatever, and you move into the FEA piece of that software, and you tell it mesh it, and it throws these things in. It usually defaults to the triangle or the tet. So it's giving you the lousiest potential element as the default. So you may want to go into the menus and say, no, no, I don't want that. I want a brick, thank you very much, and make it use that, okay? So I think that may be changing. I think with the more power, they're going to this, maybe a quadratic type element, in which case the tet and the triangular are fine. The reason they default to these two is because for very irregular shapes, it's very easy to fill those up with triangles, right? Because I can do contours and whatnot. It's harder with bricks because I end up with stepped edges and that sort of thing. So geometrically they work nice, but in an FEA sense they're not as good if I have the linear versions, okay? Another factor that makes these elements good or bad is what's called the aspect ratio. It's commonsensical. I don't want a long, skinny element that has one dimension much larger than the other. I'd like them more or less compact. And the rule of thumb they usually tell you is less than 5 to 1. So these are not good, not as good as the ones on the left, because I got more than 5 times the length to the width, and so on and so forth. Okay? There are, again, some exceptions to this. There's always exceptions, but that's a reasonable general statement. Yes, go ahead.
Also, when you're creating the mesh, it also, like, you can have a good aspect ratio, but you also have to make sure that sometimes for long, straight elements, you have more than one level of elements. So, like, most FBA programs will throw an error if you have a long beam that is only made up of single elements along the length.
Yeah, that's a good point, because you can't get information across the cross-section if you don't have multiple pieces across the cross-section. Yeah. That would not be true of line elements, but then line elements are not going to give you as much info. But I think what you're saying is...
For solid elements,
yes.
you have to have
No, you're right. You don't want one layer of bricks through your beam, is what he's saying. You want several layers of bricks, which makes perfect sense. Yeah? Thank you. So let's talk about getting the mesh right, which, again, is somewhat easy nowadays because of these automatic meshes. In the bad old days, you had to go in and create that mesh by giving it the XY or XYZ coordinates of every node of all these elements, which is a nightmare. But thankfully, that's behind us. So here I have this is right out of Chapter 8 in your book. I take a very simple problem, a cantilever beam. I stick a notch in it to make things interesting. And I put a load on the end, and I make it rectangular in cross-section, so it's very simple to calculate. Because what I'm doing here is I want to have a test case that I can solve by hand. Geometry is simple, and so forth and so on. I know the formulas. So I can find out what the classical method tells me the stresses and deflections should be in this thing for a given set of loads. And then I can compare the results from my FEA to the classical solution. And what I will do then is play with the density of the mesh until I get close enough that I don't care about the error anymore, okay? And once I have achieved that, then I can go back and go crazy with the geometry and change the shape and all this stuff to make it the real part and be reasonably confident that I'll get a good result because I have first tested it to know that I have a appropriate collection of stuff. So as I increase the density of the mesh, the stress will get closer and closer to the so-called true stress, which is what is being calculated by the classical method typically. And it's, of course, nonlinear as I make the mesh finer. So I have this example where I start with 535 elements, and then I roughly double it to 1146, and then kick it up by another bunch to 15,000, and then to almost 100,000. And we're going to recalculate the problem with each of those and see how close it comes to the theoretical number. And these are the numbers we get. So I have 2 points that I'm looking at. Point D is just a point along the beam in some arbitrary location. And point A is in the notch. And I want the point D because that's the one I can really easily compare to my classical analysis, right? Because I'm going to have to apply a stress concentration factor to that notch. And that could introduce some noise when I do the classical solution. One nice thing about FEA is the stress analysis comes out in the wash. It's automatic. It shows me it. I don't have to bother with factors of stress concentration and that stuff, okay? It's going to just show up. But it only will show up accurately if I have a fine enough mesh, particularly around the notches. So as we increase the mesh density, you see it's creeping up on the analytical solution of 3750 psi. And it doesn't start out too bad. Even with the coarse mesh, I'm at 3100, so that's off by 600, about 20% or thereabouts, maybe. Not as close as I would want to be. But I get up to my 100,000 or so, and I'm at 3713 versus 3750. That's close enough for engineering work. and maybe even the 3653 is, depending upon what your situation is, right? But look at the notch now. Don't show you the numbers here, but I have them in the example that accompanies this in the text. And I look up the Peterson's stuff for this particular arrangement of notch and size of notch and geometry and loading and all that stuff, and I get 1.56 or something like that. And we're doing a static problem here. I'm not bothering with notch sensitivity. It's just a static loaded problem. So with that number, the 1.56, I get almost 32,000 psi with the analytical method. The first shot here is like half that. And then I come up fairly rapidly to, with this very large number of elements, to be close enough for government work, certainly. So the moral of this story is, out here in the middle of nowhere where there's not much happening, I can afford a coarse mesh. But around notches, where the geometry is changing rather drastically, I need a lot of mesh. Now, I wouldn't necessarily go to this extreme in practice in which I mesh the whole thing at the same level, because I know I don't need the mesh density away from the notch. I might selectively put high density mesh around the notch and have it coarser elsewhere, and that will save me computation time at the expense of more effort to mesh it. This is a push button mesh. You know, I tell it I want so many thousands of elements, and it just does it all over the place. So that's done in 2 seconds. But in reality, you probably will have to go in and play with the mesh and locally make it finer. Yes, sir?
I took Professor Wu's class in this class.
Whose class?
Professor Wu's class.
Yeah.
Also, for a situation like that, you can exploit the symmetry part itself.
Yeah, absolutely.
So you can strain two sides that are inside the part, and then the numbers it returns are just as valid.
That's correct. Yeah, what he's saying is you can often cut the size of the problem down by, when you have symmetry, by doing a half model or a quarter model. Like that beam, we know, has the same magnitude of stress on one side as the other. They just happen to be different sign, right? So if everything else is symmetrical. So I could simply cut the beam in half down the middle and make a half model in this case. And that my computation time gets cut in half then, right? And that's often done. Here's deflection numbers. The analytical deflection, I got like 0.03 inches. And the opposite's happening here. Notice with the coarse mesh, I'm getting a pretty good number, 0.36 rather, against 0.33. And it doesn't change very much. And notice they're all higher than this number, which is interesting. So what that's telling me is that if I'm after deflections, and I don't care about stresses for whatever reason at the present moment, I can afford a coarse mesh. And the reason for that is deflection's a global property, as you should now understand from what you did this term, right? And stress is a local property. So the size of the mesh really affects the stress calculation because it's very localized. Whereas the deflection is a global overall property, so I can afford to have a coarser mesh. Okay? Now, let's puzzle over why my analytical solution is less than my finite element solution. Anyone have a suggestion as to why that might be? I'll tell you that the FEA is closer to correct, and the analytical is not. What's typically left out of a beam calculation when you do a deflection calculation? Left out of the equations.
The weight of the beam.
That often is left out, but that's not the culprit in this particular case. What kinds of stress do I have in the beam? Go at it that way. I'm sorry?
Transverse and lower?
Yeah, you've got transverse shear and you've got the bending, right? Well, it turns out that the way the equations are derived for the deflection, it ignores the transverse shear. It just considers the bending. So the transverse shear, the contribution to deflection of the transverse shear is missing from the analytical solution. And it's present in the FEA because everything's in there. So in this particular case, it turns out the FEA is a better answer. Now, if the beam is really long, you remember the rule of thumb? If the beam's more than 10 times long versus its depth, you say, the shear stress is so bloody small, I don't bother about it, just ignore it, right? But as beams get shorter than that, then it starts to be a bigger piece of the pie. And this is a fairly short beam, so it's making a little bit of difference. Not huge. You know, it's what, it's in the third decimal place, so it's not major. So we're perfectly happy with these analytical solutions unless we have a very, very short beam, in which case it could be more significant. Yes, sir?
I have a question. So like for the notch, like if the I remember like if the notch is triangular with sharp edges, and if you refine the mesh and by increasing the number of elements, the stress just goes to infinity. It doesn't converge. So like I still don't know how to do that. Like if it's triangular.
If it's triangular.
A triangular notch.
Oh, a triangular notch. Oh, now I understand what you're saying. He's saying if I have a triangular notch, real sharp notch, the stress at the corner is infinite, right? And the thing will blow up. So I think you have to probably fake it and round it off a little bit, because you can't let the stresses go to infinity. The computer won't deal with it. Yeah. But on the other hand, from a design perspective, why have you got a triangular notch? You know, because you got horrible stress concentration. I say, no, I don't want that. I'm going to put a round bottom on it to get the stress concentration down. So you know, I never encounter that problem because I wouldn't allow it in my design. Okay. And you'd be improving the design if you changed it to something more gentle, like this notch I show here. So this is a printout of the von Mises stress. That's what they're going to report to you. And there's some interesting things you can see here. These are constant stress lines, isobars of a sort. And the darker it is, the higher the stress. So you actually see the stress concentration in the notch. And you see the stresses being higher toward the root where the moment is maximum. That all makes sense. And there's very little stress out at the end, which makes perfect sense because there's no moment out there, right? Except where the force was applied. Now that was a point force, and this goes to your point. There's a point force applied to the last node on the corner at essentially a zero dimension, zero width. It's a point. And it's showing the stress concentration for the local load. You see the little dark spot in the upper right corner. This is probably with the high-level mesh. I don't remember. I didn't put a note here. Probably with a lot of elements in order to be able to see this. Now I would ignore this from a design standpoint because I know that when I put the load on, it's going to have, whatever's pushing on it's got some area. Okay? It's not literally a knife edge. So that's artifactual from my perspective. It's real from a mathematics perspective because I've got the load right on one point. Now these packages will let me apply the load over a length if I wish. And that might be a more realistic thing to do here. But I put it right on one node. And here's what I was saying earlier. The transverse shear and the stress due to bending are here. And we automatically get the stress concentration at the notch. Okay. So much for meshing. Not as big a deal as it used to be because of the automatic meshes, except for the fact that you've got to worry about making sure you got enough density around crazy shapes and notches and that sort of thing, right? Now the big bugaboo, in my opinion, in FEA is the boundary conditions. And this is where I think most of this modeling goes off the rails, particularly with beginners. And I'm going to walk you through a couple of examples here to try to point out the reasons for that. I have kind of a silly model here. I didn't want it to be a round thing, so I made a rectangular beam that is, for some reason, able to slide in rectangular bearings. Don't ask me how I would make them. But it can slide left and right, okay? So there's a whisker of clearance in there, like 1/1000th of an inch clearance in between the two so I can move it. And in addition to that, the bearings are relatively long because I want to keep the wear down. So it's not like a point support. It's a support over some distance. So the first question in my mind is, how do I model that? In other words, what kind of beam support do I have? Well, if you forget about the 1/1000th of an inch clearance, you say, it's got that beam grabbed over a good length at either end. That's like a moment joint, right? Fixed, fixed. So that would be, I think, the upper one that I show in the skeleton model there, where I'm assuming that I have a double cantilever, in essence, right? So it's in cement at both ends. Can't move. Can't change slope. At the other extreme, it's simple supported, as if this thing had no length at all. It's just sitting like there or someplace. And that's the classical way you'd describe that, is with a pointy thing on one end and a round thing on the other, so I don't put any, if it stretches due to thermal expansion, I don't do anything bad to it. It can roll on the roller, yeah? So here's simple support. There's cantilever type support, or fixed. And the question is, which of those is more appropriate, or is either appropriate? And as you might expect, the answer is neither of those is going to give me the correct answer. The truth lies somewhere in between. These are the two extremes, and I'm going to be somewhere in the middle, probably closer to one than the other, but that will depend on a whole bunch of things. And the problem is that my FEA modeler is very, shall I say, anal compulsive. If I tell it that those nodes are fixed, in other words, if I create that bearing by telling it those nodes along that length cannot move, by God, they can't move. There is no give whatsoever. But if I really buried that in concrete, the concrete could give, couldn't it? So there's no such thing in the real world as a true fixed joint or fixed joint, because that assumes that the building that it's on and the ground don't move at all, right? Well, for most applications, that's a safe assumption, because I got 100 pounds on the beam, the building weighs 80,000 tons, and there's Mother Earth under me. So, I'm not going to fret over that sort of thing. But nevertheless, the FEA is going to think everything is perfect. So let's look at what kinds of results we get. So simple problem, I can solve it by the classical method, and I do that with the appropriate equations. And for the fixed supports, I see something that looks like this for deflection. It's about 3 10,000ths of an inch, or 4 10,000ths of an inch with the other figure, and about roughly 3 times that, or 2.5 times that, with the simple support. Now, you should expect that you would get more deflection with simple support, right? Because the beam can change slope at the supports. And when I lock that thing in concrete, it can't change slope, so it can't bend as much, and I stiffen the system. So my choice of boundary conditions makes a huge difference in the way, or the answer that I get. So I got to be careful that I apply appropriate conditions to my FEA model, otherwise I could get a very wrong answer off by a factor of 3. So now we're going to do it both ways with the FEA modeler. So the first one I'm going to do here is a simple support, and I ask myself, if I'm going to represent that bearing as one load, where would I put it? Should I put it in the middle of the bearing, on the right end, the left end? And it seems sensible to me that the insides would be where it would be, because as the beam bends, it's going to essentially pivot at those corners. That make sense? So I tell the solver that those corners are fixed, and it can't move in Y. I actually tell the left one, let's say, that it can't move in either X or Y, and I tell the right one it can only not move in Y, but it can move in X. And that's my roller, right? The little pointy thing in my theoretical model, which is off the screen now, is fixed in X and Y. That's stuck to the beam. The other end's on a roller, so X is not constrained. Okay? And I do that calculation, and I get that number, which I think we already saw. Then I do the fixed, and I get a number that's not exactly the same as the other one, 0.32 instead of 3.6, I think it was. So there it is right there. So it's very close. And notice the stress concentrations right there. And notice the stress concentrations at the end of the bearing. That is consistent with what we talked about when you have a roller running over something, and where the roller stops, you get a stress concentration, right? Same concept here. I still haven't resolved the issue as to which of these is correct. But notice that it's hard to see, but I show a little bit of white space in there. Because in this particular case, the deflection was not sufficient to cause this to curl up so far that it hits the other side of the bearing on the top. And if it does, that's going to change things very dramatically, right? Because now I'm switching from a simple support to a fixed type support. But I've already baked in some slope. So it's not like it started out fixed. So what I'm going to do now is introduce a more sophisticated boundary constraint. And most of the solvers will have something of this sort. It's called a contact condition or a contact constraint. And very simplistically what it means is I'm going to be able to tell the solver that these two things cannot move together any further than that, but they can pull apart. Okay? It's like a gear tooth on a gear tooth or a cam roller on a cam or anything of that sort. It's a true kind of constraint that we have physically in nature. Yeah? And mathematically, these things will simulate that, so it tells that you can't go that way, but you can go this way. And that's different than telling it that that node's pinned, right? So now I do that calculation with two different load sets. The same 250 I used before, and I get, no surprise, the same answer. But then I crank the load up to 1,000 pounds, and that's enough to deflect it sufficiently to see the beam hit this other corner at A prime. I rounded those to reduce the stress concentrations, by the way. So I've switched the thing over to essentially a fixed system on the fly by reason of the deflection. So you see the advantage of the contact constraints. I don't know what kind of load I'm going to have when I start this out. I want this to be able to solve for any load at all, right? So this takes care of it. It comes out in the wash. Okay? So these are very handy. Now we have a similar situation when we have things supported on pins, which is very common. That's a lever from a machine, which maybe is cam-driven or something. And so it is, in fact, a cam-driven link. So it's pivoted over here. This R2 represents the cam. There's actually a roller here against the cam. Don't show the roller. And then over here is a connecting rod going upstairs to something or other. And I've made everything symmetrical in this view to keep things clean, so all the forces are in line with the centroids and whatnot of the cross sections. So I don't have any torsion and all that stuff. And I want to do an estimate of this with FEA. Now, I think one's first instinct would be, since I have a pin and a hole, in my analytical model, I pretend there's a force at the center of the pin, right? And the pin somehow distributes that around the hole. There's really line contact, but then there's some deflection, and I get a little bit of a contact patch, right? And I don't even know or care in the analytical solution what that business is, because theoretically I have a point load or support at the center of the pin, right? Unless I'm interested in the stresses between the pin and the hole, I don't care about any more than that. So I think one's first instinct might be to pin down all of the nodes around the hole in X and Y, for example, and that turns out to give me a very erroneous answer, because unlike the true thing sitting on a pin, which when it starts to deflect can rotate around the pin, I've just eliminated the rotation by telling the circumferences of the holes they can't move, right? So I've stiffened the system, much like the fixed in the other example. So here is that condition. I call them circumferential constraints. So you go in and you tell every one of those nodes that can't move in X and Y. Then you apply the load, and this depicts the undeflected mesh in black and the deflected in color after the computation is done. And as you would expect, you told these points they couldn't move, and they don't move. And I get that condition. Now, if I do something different, every FEA package I've come across calls this something different, does it in a little bit different fashion, but they all end up doing the same thing. In essence, what I want to do is be able to put my constraint at the center of the pin. But there isn't a pin. It's a hole. So there's nothing there. So there's nothing I can put on my model if there's nothing but air there. So we put a node in the middle of the center of the circle, and we declare that to be unmovable. And then we connect that node up with what I call them bicycle spokes. So we have these bicycle spokes going up. These are elements. They're rigid body elements, so they have no deflection possible. Okay? And they're each connected to a different node around the hole. You don't see these in your model, but that's what's happening behind the curtain when you choose this particular constraint in this particular package. This is an abacus. And SolidWorks calls it something different, doesn't talk about spokes in its description, but it's going to do the same thing. Now when I do the analysis, notice that I am actually seeing a shift rotationally, and the thing is rotating on the pin. And I think I show you some numbers here. So if I use the first method, which is not the one I want, I get roughly 5 thousandths of deflection. If I use what Abacus calls kinematic coupling constraints, I get 6.6, and my analytical tells me 6.4. And again, the analytical is lower because I don't have the transverse shear in it. It's not in the equation. But that's close enough for me. But the other's a factor of 2 error. No, factor of 1.5 maybe. Okay? So boundary conditions are extremely important. And that's where I see the most errors being made in FEA, and not just by students. I'm often called in as a consultant to look over a design package of some sort where they've done extensive FEA. I did this just about a year ago for a big company locally for a truck transmission. This is a monster truck like they use in the open pit mines. You know, it's twice as tall as this room. The tires are up to here, this sort of thing. It's just enormous. You can put 3 dump trucks in the back of it, 3 regular dump trucks. It's that big. And as it turned out, I found an error in their FEA, and it had to do with boundary conditions. And also it had to do with they were ignoring some other issues. But boundary conditions were the main issue. And the axle would have failed. So they made it bigger, and they solved the problem. So here's another thing we can do with FEA. This is a different issue altogether, called modal analysis, the fancy name, finding the natural frequencies and more. Because by modes is meant the shapes of how it bends when it vibrates. And there'll be a whole bunch of these modes, you know, first harmonic, second, third, fourth, etc. And they won't be equispaced in frequency either. They will not be double, triple, quadruple. They'll be in some staggered increments. And they're all shown here in hertz. So this is an example. This is an actual part out of a Gillette machine. And again, it's a cam follower arm. And I have 2 designs, one of which is unpocketed, meaning it doesn't, I should show you what the pockets are so you can tell. Oh, I didn't show you that slide. That's too bad. Well, I'll have to fake it. This had pockets relieved into it to reduce the mass, because it's moving pretty fast. And in the book, I do an example where I do it for both. And I show that when you take the meat out for the pockets, you really do a number on the natural frequency, as you would expect, because I'm taking out mass and I'm reducing stiffness, both. But all this slide is showing you that I can get as many bending modes as I want. This is showing the first 3. So this tells me that the fundamental frequency of this part in bending is 104 hertz. The second is 455, well more than double. The next one is 620, less than double. So they're oddly spaced. And I could keep going and get higher ones and higher ones. And that now tells me that I don't want any forcing frequencies in my, whatever I'm driving this thing with, to sit at any of those frequencies, because it's going to make it go crazy in resonance, right? So having this information is really useful in order to avoid vibration problems. And this is done more or less the same setup. Your boundary conditions have to be correct. Your mesh, well, in this case, you can have a sloppy mesh, because this is a deflection type characteristic, so it's global. And so having a coarse mesh doesn't make these numbers very inaccurate. So if I'm only after a modal analysis, I don't have to mesh the dickens out of the thing, because I'm not looking locally at stresses and so forth. Okay? So to sum up then, it's a very powerful tool. And like any powerful tool, you can get powerfully wrong answers out of it. It handles the complex geometry. That's the beauty of it. And in combination with a CAD system, and they're all married to CAD systems because you can take your CAD model and move it over into Abacus or ANSYS or whatever and mesh it and turn the crank and put your boundary conditions in and get your results very nicely. I get stress, deflection, and modal information out of it. I can get really good answers if I'm using it right, and I can get really bad answers if I'm not. So you've got to use it with care. And what you always should do is you start with a simple model. I got a crazy link of some wild shape or other, and I want to model that and analyze it with FEA. So what I'm going to do first is I'm going to make up a model of a simple shape. Maybe it's rectangular, round, and cross-section, something I could actually do by hand that's similar in size and so forth to the real part. But I'm going to simplify the geometry so I can actually do a hand calculation. And then I'm going to set that model up with what I think are the right boundary conditions. And I play with the boundary conditions until I get the same sort of deflection I'm getting in my analytical model. And now I know I've got the boundary conditions approximately correct. Now I can go hog wild with the geometry and change the shapes. If I keep the boundary conditions the same, I should be okay. Right? So it's critical to do a test case that is simple enough for you to do by hand as a check, and then go at it with the change in geometry, and you'll be fine. This is the way things are being done in engineering offices all over the world now. They do it to the whole car body. I've seen this done out at Chrysler. It's absolutely amazing. They have a model in CAD. They were using CATIA, which is another big gorilla of CAD packages. And I can't remember what they were using. I think Nastrian they were using for the analysis part of the FEA. And they literally have the entire body of the car modeled in CATIA, and all the components, the engine, suspension, the whole thing has a big assembly. And they can go in that and run Nastrian on the body shell and find out what the modes of the body shell are. And then they can determine whether or not they have excitation frequencies in the engine at whatever speed that are going to cause that whole body shell to buzz like a drum, right? And they're trying to get out the NVH, the noise, vibration, and harshness, and they've done a marvelous job. I mean, the cars now are so much better in that regard than they were even 20 years ago. And it's largely because of this ability to do this very complicated modeling with the combination of CAD and finite elements to not just find the modes, but the stresses and the deflections. So you look for hot spots in the design of the body, and they come back and redesign, add more metal here or there or whatever, until they get it so it doesn't fail. And that's why these systems are so reliable now. And the aircraft company were doing this the longest of anyone. In fact, the first CAD systems that were developed that were serious 3D CAD systems, one was by McDonnell Douglas, now part of Boeing. The other was by Dassault in France, Mirage jet fighter. One was called Unigraphics, was the buzzword for McDonnell Douglas, and CATIA was the word for Dassault. That's still sold as CATIA. Unigraphics has changed its name 3 times. It's now called something else. I've forgotten what it is now. And McDonnell Douglas sold it off, so it's owned by a separate company. But these packages, we're talking CAD solid modelers now, were created for the purpose of designing airframes because they were too complex to do with manual calculations. You got wings with crazy airfoil shapes and tapers and whatnot, and the fuselage likewise. In parallel, others were developing FEA code, and they married those two, and that's why you can get away with 1.1 for a safety factor in an aircraft and not kill everybody, because the accuracy of the analysis is so good. But it takes a lot of effort and a lot of time and a lot of money. So that's as much as I'm going to say about that. I'm going to stop now and ask you to do the course evaluations. I'll give you plenty of time to do that. Yes, Robert?
You said that we should try and avoid like the triangles and the tats. How? I understand that each of those shapes is something that would come out of your 2D or 3D shape, and that would just, each of those points would be nodes connected to other shapes. How would you avoid those shapes coming out of
I think what you're asking is you have a really weird shaped part. How do I make it all into bricks?
Right.
Whereas if I have those triangular thingies, I can go around a hole very nicely. That's why they're handy. It turns out you can do the whole thing with bricks. You just have to make very small bricks around the hole. And your hole then becomes straight-sided rather than looking more, well, it's straight-sided anyway, because you're going to have triangles with the back sides on the inside of the hole. You're going to get an approximation no matter what you do, right?
And that would just be the advantage of using more and more.
Yeah, it costs you more in the computation time. But see, on the other hand, the computers now have become so powerful and so fast that it's almost a non-issue. You had a question.
Yeah, like FEA will give you your RBC stress, your principal stresses, so finding out if it will fail and anything with G loading is still done by hand?
Yeah, pretty much. Pretty much. You take those numbers to a Goodman diagram, essentially. But now you've got presumably good numbers to take to the Goodman diagram, right? That's the big advantage of it. You've got good numbers if you were careful about the boundary conditions. All the cases I've run into in recent years in which I've been asked to check something, I did one over Christmas, they did an FEA analysis. In one case, they screwed up the boundary conditions, and the results were wrong. So the first thing I always check is the boundary conditions. What do they do for that? And sometimes it's quite obvious, because if you look at the deflection plot and you expect that there's a pin support at that place and you see zero slope on both sides of it, there's something wrong. I should not have zero slope across a pin, right? It should be going either like this or like that or like this. And as soon as you see that in the plot, you say there's something wrong. So you have to check that from a common sense standpoint as well. I don't want to take up your time. I want to leave you 10 minutes to do this. Any other final questions? Yes, sir.
How does it handle? I mean, all those examples of the applied loads are simply, point loads.
Oh, you can do anything you want. You can put distributed loads on.
Yeah, I was wondering how you model.
You can put they have all these features built in. You can have, I want an internal pressure in this vessel. It'll give you uniform pressure in all directions. Or I want a uniform load over this distance of whatever. Or I want a load that grows. All of that stuff is built in. So you have to find out how they are doing that and apply it. But yeah, you can have realistic loading very nicely.